Welcome to everyone. This is Dr. G. Pawan Kumar, Assistant Professor, Department of Physics, St. Joseph College for Women, Visakhapatnam. Here we are discussing about the first BSc second semester Unit 2. Topic name is Mechanics of Particles. Content of the second unit: Newton's first law, Newton's second law, Newton's third law, system of variable mass, motion of rocket, conservation of energy and momentum, collisions in 2 and 3 dimensions, impact parameter and scattering cross section, Rutherford's scattering derivation. In second unit, we are able to study the relationship between the motion of an object and the force acting on it. Newton's first law: an object remains at rest or uniform motion unless acted upon by an external force. Newton's first law is also known as law of inertia. When object is at rest, velocity v is equal to 0 and acceleration a is equal to 0. Therefore, the object continues to be at rest. Suppose an object in motion, velocity is not equal to 0, acceleration is not equal to 0. Therefore, the object will continue to be in motion with constant velocity and in the same direction. Newton's second law: the time rate of change of momentum of a particle is equal to the net force acting on the particle and it takes place in the direction of the applied force. F is equal to dp by dt. Our second definition is the applied force is directly proportional to the product of the mass and acceleration of given body. That is equal to F is equal to ma. Newton's third law: to every action there is an equal and opposite reaction. Suppose F12 is force acting on a body 1 due to body 2. F21 be the force acting on a body 2 due to body 1. So F12 is equal to minus F21. Next topic is system of variable mass. The system in which the total mass remains constant. Such systems are known as isolated systems. Here we are studying about the variable mass system. That means a system in which mass changes with the time. So let us consider a system of mass m whose center of mass is moving with a velocity v at any instant of time t. Later, the time t plus delta t, a mass delta m has been ejected from the system. Its center of mass moves with a velocity u. Now, the system of mass reduced to m minus delta m and the velocity of the system is changed to v plus delta v. The above problem may be solved by applying the Newton's second law to the combination of the two masses, that is the remaining mass m minus delta m and the ejected mass delta m combine to form the whole mass of the system. We know that Newton's second law of motion with respect to the momentum, F external is equal to dp by dt. For small intervals of time, F external is equal to delta p by delta t. So delta means the change in initial and final momentums. So this can be written like this: pf minus pi by delta t. Considering both the parts of masses delta m and m minus delta m as forming the whole mass and the same system. So we can write F external is equal to pf minus pi by delta t is equal to m minus delta v into v minus delta v plus delta m into u minus mv by delta t. That is equation 1. Here Pf and Pi are the final and initial moments of the system. After solving the above equation, we get F external is equal to m into delta V by delta T minus V delta M by delta T minus delta V into delta M by delta T plus U delta M by delta T. That is equation 2. If delta T approaches to 0, the configuration on right side approaches to left hand side. That is, delta V by delta T approaches to 0, it becomes a dV by dt. That means the acceleration of the body. Since there is a decrease in mass with the time, hence delta m by delta t is replaced by minus dm by dt as delta t approaches to 0. Delta v goes to 0, delta t approaches to 0. Making these changes in equation 2, we get F external is equal to m dv by dt plus v dm by dt minus u dm by dt. So this can be, the above equation can be written like this: F external is equal to d by dt of mv minus u dm by dt. That is equation 3. Equation 3 expresses the Newton's second law as applied to a body of variable mass. It is obvious from the equation d by dt of mv is not equal to the external force acting on the system unless the ejected mass comes out with 0 velocity. So from equation 3, F external is equal to m dot dv by dt plus v dot dm by dt minus u dm by dt can be written like this: m dot dv by dt is equal to F external plus, here we are taking dm by dt is a common, u minus v. So that is equation 4. Equation 4 is the rate of change of momentum of the system due to mass leaving it. This can be recorded as the reaction force exerted on the system by leaving the mass. For rocket, this term is called as the thrust. So the above equation can m dv by dt is equal to F external plus F reaction. Next topic is motion of rocket. It is the best example for the system of variable mass. The rocket consists of a combustion chamber in which liquid or solid fuel is burnt. In the rocket, the fuels like liquid hydrogen or liquid paraffin and the suitable oxidizers like oxygen or nitric acid are stored in a separate chambers or injected into the combustion chamber, while in the latter the fuel and the gunpowder, which is itself carries its own oxidizer from a single chamber, is injected in the combustion chamber. When the fuel is burnt, the pressure inside the chambers rises very high. Due to high pressure inside the combustion chamber, the hot gases are expelled from the tails of the rocket. The expelled gases are in the form of a jet with high exhaust velocity. Consequently, the rocket rushes in opposite direction to the direction of escape of gases. The motion of the rocket explained by the Newton's third law of motion and law of conservation of momentum. Let capital M be the mass of the rocket including fuel and v be the velocity at any time t. Let a time interval dt, the amount of mass delta m is ejected from the rocket in the form of gas jet. Suppose minus u is the velocity of the gas jet with respect to the rocket, the velocity of the gas jet will be v minus u. Let v minus u is equal to v real. The rate of change of momentum of jet issuing out of the rocket, that is force acting on the rocket, is equal to rate of change of mass of the rocket due to escape of hot gases into velocity, that is equal to dm by dt into v minus u. From the Newton's third law of motion, this is equal to the thrust on the rocket tending to move it in the forward direction. That is thrust acting on the rocket to move it forward direction. So that's why T is equal to dm by dt into v minus u. Let Fxnl be the force acting on the rocket. Here Fxnl is equal to minus mg. Mg means the total weight of the rocket. Next, the force acting on the rocket in forward direction can be written like F external is equal to dm by dt into v minus u minus mg, that is equation 1. From the Newton's second law, the force acting on the rocket F is equal to d by dt of mv. From equations 1 and 2, we get d by dt of mv is equal to dm by dt v minus u minus mg. Left hand side we are applying uv formula, right hand side we are multiplying the terms. We get m dv by dt plus v dm by dt is equal to v dm by dt minus u dm by dt minus mg. After cancelling the above equation, so m dv by dt is equal to minus u dm by dt minus mg, that is equation 4. The equation 4 represents first law, first rocket equation. After that, so we are dividing with respect to the mass m. We get dv by dt is equal to minus u dm by dt minus g. Consider the magnitudes of v, u and g. We get dv is equal to minus u dm by m minus g dt, that is equation 5. Integrating the equation 5 in between 0 to maximum points, that is integral v naught to v dv is equal to minus u. Here mass will be changed from m naught to m, so that is integral m naught to m dm by m minus g. Time will be changing from 0 to certain time t, so that's why integral 0 to t dt. So after integration we are getting final equation is v minus v naught is equal to minus u log m by m naught minus gt, that is equation 6. Equation 6 represents the velocity of the rocket at any time t. This is second rocket motion. Special cases: 1. If the force of gravity ignored, then v minus v naught is equal to minus u log m by m naught. Case 2. If the initial velocity of the rocket is 0, then v is equal to minus u log m by m naught. Next topic: conservation of energy. The energy can neither be created nor be destroyed, although it may be transferred from one form to another form. Suppose conservative forces operate on a system of particles. If UF and UI be the potential energies and W be the work done, then UF minus UI is equal to minus W. But we know that by the work energy theorem, the total work done is equal to kinetic energy. So that is W is equal to KE, that is equal to KF minus KI. So here the two total work done of the potential and kinetic energies will be equal. So UF minus UI is equal to minus of KF minus KI. So we are separating the final and initial energies. So UF plus KF is equal to UI plus KI, that is equation 1. The sum of potential energy and kinetic energy is called as the total mechanical energy. Equation 1 shows that the total mechanical energy of the system remains constant. Let us consider the body of mass m and height h above the ground. At a position A, the kinetic energy of the particle or a body will be 0 and the potential energy is mgh. The sum of the two energies gives the total energy, that is mgh. Now the body falls through a distance x where the velocity of the body becomes v. So we know the formula v square minus u square is equal to 2ax. So by using that equation, here we are writing v square is equal to u square plus 2gh. We have the velocity v is equal to root 2gx because u is equal to 0. The kinetic energy of the body half mv square is equal to half m v square means 2gx. After solving we get mgx. Potential energy of the body is equal to mg into h minus x. That means mgh minus mgx. So the sum of the two energies will give the total energy. So that is mgh. So the principle of conservation of energy may also be stated as the total energy in any system is always remains constant. Conservation of momentum. When no external force acting on an isolated system of particles, then the total momentum of the system remains constant. We know that P is equal to mv. Here we can write like this: P is equal to mvcm. mvcm represents the velocity of the center of mass of the system. Differentiating the above equation, we get dp by dt is equal to m into d by dt of vcm, that is equal to m acm. acm represents the acceleration of the center of the mass. We know external force F external is equal to ma. Equating the above two equations, dp by dt is equal to F external. The above equation shows that the rate of change of momentum of system of particles is equal to the vector sum of all the external forces acting on the system. When no external force acting on the system, F external is equal to 0, dp by dt is equal to 0, that is P is equal to constant. So that is P is equal to sum of the individual moments of P1 plus P2 plus P3 up to so on. That means P is equal to constant. It represents the law of conservation of momentum. Next topic is collisions. A redistribution of total momentum of bodies or particles when they approach each other. So these are the different type of collisions: perfectly elastic collision, inelastic collision, semi-elastic collision. Perfectly elastic collision means when the kinetic energy of the particles remains constant or conserved in the collision. The collision is said to be elastic. The collision between the atomic, nuclear, and fundamental particles are the best examples for the perfectly elastic collision. In elastic collision, conservation of momentum and the conservation of kinetic energies hold good. That is, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So kinetic energy can be written like this: half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. Next one is inelastic collision. When the kinetic energy is changed in the collision, the collision is said to be inelastic. Example: in elastic collision, the momentum as well as the total energy is still conserved. Examples for the inelastic collision: first one, grass bodies are always inelastic. A bullet is embedded in a target. Next, in an elastic collision between the large particles, the loss of kinetic energy occurs in the form of heat. Suppose the electron in lower energy state absorbs some energy and moves to higher energy state, that means excited state. The energy absorbed by the electron is known as excited energy, is expressed as zeta. Thus, the final kinetic energy of the system is less by this amount. Hence, we have half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square plus zeta. The electron is already is in excited state before collision. Return to its normal state, it releases the potential energy zeta absorbed during the excitation. Hence the equation can be written like this: half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square minus zeta. Next one is semi-elastic collision. The collisions fall between perfectly elastic and perfectly inelastic collisions are called as semi-elastic collisions. In these collisions, a part of total kinetic energy is lost during the collisions. That is, kinetic energy is not conserved all through, the total energy is conserved. The loss of kinetic energy in such collisions is not sufficient to the extent the bodies stick together as in case of a perfectly inelastic collisions. Consider the case of two bodies of masses m1 and m2 moving with uniform velocities u1 and u2 and colliding each other. Let their velocities will be v1 and v2 respectively. For semi-elastic collisions, we have E is equal to relative velocity of separation after collision by relative velocity of approach before collision. That is, E is equal to v2 minus v1 by u2 minus u1, or v2 minus v1 is equal to E into u2 minus u1, where E is called the coefficient of inelastic collision or restitution. Restitution means the ratio of the absolute value of the relative velocities of the bodies after and before collision. if E is equal to 1 for perfectly elastic collisions. Next topic is impact. That means it is a high force or shock applied over a short time period when two or more bodies collide. It does not provide sufficient time for these deformations and vibrations to occur. Second one, line of impact. When two bodies collide, their surfaces are in contact during collision. If a line is drawn perpendicular to the common tangent to the surface at that point of contact, the line is called line of impact. Second one, direct impact. When the centers of masses of the colliding bodies are initially moving along the line of impact, then the impact is called as direct impact or head-on collision. Note, after direct impact, the bodies continues to move along the line of impact. This can be shown in the figure. Next one is oblique impact. When the center of masses of the colliding bodies are not initially moving along the line of impact, then the impact is called oblique impact. This can be shown in the figure. In the previous class we are studying about the collisions in one dimension. Here we are studying about the collisions in 2 and 3 dimensions. In 2 and 3 dimensions, the two conservation laws like conservation of kinetic energy and conservation of momentum alone cannot tell us the motion of particles after a collision. In the below figure, the distance b between initial line of motion and a line parallel to it through the center of target particle is called impact parameter. If b is equal to 0 corresponds to head-on collision. After collision, the particle m1 makes an angle theta 1 with the initial direction, while the target projectile m2 initially at rest moves in a direction makes an angle theta 2 with the initial direction of incident projectile. Applying law of conservation of momentum, m1 v1i is equal to m2 v1f cos theta 1 plus m2 v2f cos theta 2. That is equation 1. 0 is equal to m1 v1f sin theta 1 minus m2 v2f sin theta 2. That is equation 2. Considering the collision to be elastic, the conservation of kinetic energy gives half m1 v1i is equal to half m2 v1f plus half m2 v2f. All these are shown in the below figure. Previously we are discussing about the different type of collisions in 1 dimensional, 2 dimensional, 3 dimensions. By using the collisions, Rutherford trying to explain the size of the nucleus by his Rutherford's alpha scattering method. Here we are discussing about the Rutherford scattering. Consider a nucleus of charge Ze rest at a point L and alpha particles of masses m, charge 2e and velocity v0 approaching along the direction AO as shown in the figure. With this result, the velocity of the alpha particles decreases. In the absence of repulsion, it would have followed a straight path, but due to Coulombic force of repulsion, it follows a hyperbolic path. that is ACB, with the nucleus as its focus. The line AO and PO are initial and final directions of alpha particles. In the path of journey AC, the velocity of alpha particle goes on decreasing, while in the part CB, its velocity goes on increasing. P is the perpendicular distance from the nucleus N to the original direction of the particle. This distance is called as impact parameter. The closest distance approaches to the nucleus and a perpendicular line drawn from the original path is called as impact parameter. At this time, the alpha particle makes an angle. Here, the angle of deviation or scattering angle phi. This can be measured by two cases. In case 1, if p is equal to 0, the alpha particle will be stopped at a distance b from the nucleus due to repulsive forces and trace its reverse path, that is pi is equal to 180 degrees. The distance b is known as distance of the closest approach. The value b can be determined by the principle of conservation of energy. The electrostatic potential at a distance b due to the nucleus is Ze by 4 pi epsilon naught b. Hence, the potential energy of the alpha particle at a distance b from the nucleus is Ze by 4 pi epsilon naught b into 2E. So that is 2 Ze square by 4 pi epsilon naught b. When the alpha particle is momentarily stopped at a distance b, its kinetic energy is completely converted into its potential energy. So that's why half mv naught square is equal to 2 Ze square by 4 pi epsilon naught b. So b is equal to Ze square by pi epsilon naught mv naught square. That is equation 1. Case 2, if p is not equal to 0, that means the alpha particle is deflected through an angle which is less than 180 degrees and transverse a hyperbolic path. Here, v be the velocity of the alpha particle at the vertices C. The velocity v can be calculated by applying the law of conservation of angular momentum. So that is angular momentum of alpha particle at A is equal to m v naught p. Angular momentum of alpha particle at C is equal to mv into nc. nc means d. So that is equal to m v naught p is equal to m v d. So v is equal to v naught p by d, equation 2. Now p can be calculated by applying the law of conservation of energy. Why? Here the alpha particles are moving, that way we are using law of conservation of energy here. And it is moving in a hyperbolic path ACB. So that's why kinetic energy of alpha particle at A is equal to half mv naught square. Kinetic energy of alpha particle at C is equal to half mv square. Potential energy of alpha particle at C is equal to Ze into 2E by 4 pi epsilon naught d, that is equal to 2 Ze square by 4 pi epsilon naught d. We know that law of conservation of energy, that is half mv naught square plus 0 is equal to half mv square plus 2 Ze square by 4 pi epsilon naught d. So v square is equal to v naught square minus Ze square by pi epsilon naught mv. So here v square is equal to v naught square minus b v naught square by d. So I am substituting the b value here. Next one, v square is equal to v naught square into 1 minus b by d, that is equation 3. Substituting the value of v from equation 2 in equation 3, we get v naught square p square by d square is equal to v naught square into 1 minus b by d. After solving, we get p square is equal to d into d minus b, that is equation 4. By using properties of hyperbola, we can calculate the d value. So that is eccentricity of hyperbola E is equal to secant theta, focal length ON is equal to EOC, that is equal to A secant theta. From the figure, ON is equal to P cosecant theta, A is equal to P cot theta. We know that NC is equal to NO plus OC. I am substituting the above values here. So after that, we are getting NC is equal to P into cot theta plus 1 by sin theta. Taking LCM, after solving the equation, we are getting D is equal to P cot theta by 2, that is equation 5. Substituting D value in equation 4, we get P square is equal to P cot theta by 2 into P cot theta by 2 minus B. We get final equation. Final equation is B is equal to 2P tan pi by 2. Tan pi by 2 is equal to B by 2P. Substituting the B value here, tan pi by 2 is equal to ZE square by 2 pi epsilon naught m V naught square P. This equation determines the scattering angle pi. It is clear that the smaller the value of P, greater will be the scattering angle if other quantities remains same. Next one, Rutherford's cross section. Let small n be the number of atoms per unit volume of the scatterer of thickness T. The scattered particles are detected by means of scintillation produced by them on the fluorescent screen S. Let Q be the total number of alpha particles that strikes the unit area of the scatterer. It is clear that any alpha particles whose initial velocity would bring it within a distance p of the nucleus will be deflected through an angle phi. Let a circle of radius p drawn around the nucleus. The area occupied by all such circles in unit area of the foil is pi p square nt. The portable number of alpha particles coming within the distance of an impact parameter p of nucleus is given by pi p square nt cube. Hence, the number of alpha particles having an impact parameter between p and p plus dp is given by d of pi p square nt cube, that is equal to 2 pi p nt cube dp, equation 8. It is used to calculate the Rutherford's scattering formula. Now, the scattering cross-sectional sigma is given by sigma is equal to number of alpha particles scattered into solid angle per unit time by incident intensity. Solid angle between pi and pi plus d pi, d omega is equal to 2 pi sin pi d pi. The number of alpha particles scattered into solid angle d omega is given by sigma I d omega is equal to sigma I 2 pi sin pi d pi, that is equation 9. This should be equal to the number of incident alpha particles having impact parameter between P and P plus dP. The area between circles of radii P plus dP and P is given by d of pi p square is equal to 2 pi p dP. Number of incident particles is equal to 2 pi p dP into I, that is equation 10. From equations 9 and 10, so we can write sigma I 2 pi sin pi d pi is equal to minus 2 pi p dP I. I is the incident intensity. The negative sign shows that an increase in P cause a decrease in pi. Hence, sigma is equal to minus 2 pi p dP I by I 2 pi sin pi d pi, that is equal to minus p dP by sin pi d pi, that is equation 11. From equation 7, we get P is equal to ZE square by 2 pi epsilon naught m V naught square cot pi by 2. So dP is equal to ZE square by 2 pi epsilon naught V naught square. So cot pi by 2 means here minus half cosecant square pi by 2 d pi. Substituting the above values in equation 11, we get final equation sigma is equal to z square e power 4 by 16 pi square epsilon naught square m square v naught power 4 sin power 4 pi by 2. This represents the Rutherford's scattering cross-sectional area formula. So this is another topic. So here we are calculating the Rutherford scattering formula. So first equation we are able to find out the phase difference theta value, and next one Rutherford scattering cross sectional area, and the third one is the Rutherford scattering formula. So according to equation 8, the number of alpha particles having an impact parameter between the P and P plus dP is given by 2 pi P and TQ dP. Substituting these values in equation 12, we get the number of particles scattered between angles pi and pi plus d pi, that is 2 pi NTQ into ZE square by 2 pi epsilon naught mv naught square cot pi by 2 into ZE square by 2 pi epsilon naught into v naught square into minus half cosecant square pi by 2 d pi. All these alpha particles will strike the screen within a circular annulus of area dA is given by dA is equal to 2 pi r sin pi r d pi, that is equal to 2 pi r square sin pi d pi, that is equal to 4 pi r square sin pi by 2 cos pi by 2 d pi. After substituting the values in the above equations, we get n is equal to qnt z square e power 4 by 16 pi square epsilon naught square r square m square v naught power 4 sin power 4 pi by 2. This is known as Rutherford's scattering formula.